All right, welcome back. Today, we're going on an absolute mind-bending journey into some of the most extreme space physics imaginable. In this explainer, we're going to unravel a massive cosmic mystery, one that bridges the gap between the vast, violent expanse of the universe and, well, the everyday objects we hold dear. We're talking about stellar deaths, objects so dense they literally bend light, and the ultimate cosmic forge.
I mean, seriously, take a second and think about the gold in your jewelry, or even the tiny bits in your smartphone right now. Where did it actually come from? We mine it from the Earth, sure, but our planet didn't create it. The Earth just cannot forge elements that heavy. In fact, to make gold, you need conditions so unbelievably violent and extreme that they almost defy human comprehension. Today, we're going to explore exactly how multiple Earth masses of solid gold are created in mere minutes out in the dark stretches of space. So hang on to that thought because the answer is entirely out of this world. Part 1. The Mystery of Cosmic Gold. To start our cosmic detective arc, we really have to rewind the clock. We need to look at the life cycles of the massive stars responsible for forging the building blocks of our universe. Because before you can make gold, you have to understand how stars survive, and more importantly, how they die. You see, stars survive through nuclear fusion, constantly battling the crushing inward pull of their own gravity. They kick things off by burning hydrogen, and that phase can last for millions or even billions of years. But once the hydrogen runs out, the star has to switch to helium. That's less efficient, so it lasts maybe less than a million years. Then, the timeline catastrophically shrinks. Carbon and oxygen burning, that might only last a few hundred years. By the time the star is frantically fusing silicon to make iron, it's got a handful of hours left to live. The star's fuel depletion drastically accelerates as it desperately tries to prop itself up.
Okay, let's dive into this, because this is where everything goes horribly wrong for our massive star. Fusing lighter elements releases energy, right? That energy pushes outward and keeps the star inflated. But iron is the ultimate cosmic dead end. Hitting iron triggers a catastrophic collapse, simply because fusing iron doesn't release energy. It actually absorbs it. Suddenly, there is absolutely no outward pressure. Gravity, which has been waiting patiently for millions of years, finally wins. In a matter of seconds, the entire star collapses inward at a substantial fraction of the speed of light, resulting in one of the universe's most spectacular explosions, a supernova.
Which brings us to part 2, the ultimate gravity trap.
While the supernova explosion blasts the star's outer layers across the cosmos, we need to focus our attention on the core that gets left behind. We're transitioning from the fiery death of a star to the bizarre, terrifying object left sitting in the wreckage. Meet the neutron star. Now, this extreme concept was actually first proposed way back in the 1930s by physicists Walter Batty and Fritz Zwicky. They realized that the end result of a supernova could be an extremely dense core made almost entirely of neutrons. The pressure during the star's collapse is so immense that electrons are literally forced inside atomic nuclei, smashing into protons to become neutrons. The only thing keeping this star from collapsing all the way into a black hole is a wild quantum mechanical quirk called neutron degeneracy pressure. Basically, it just prevents neutrons from being squeezed too closely together. To really grasp what a neutron star is, consider this completely mind-bending contrast. Imagine taking up to 2.2 times the mass of our entire sun, a star that is already over 1 million times bigger than Earth, and crushing all of that massive weight down into a sphere that is only a few kilometers across. We are talking about an object with a mass of multiple suns packed into a space roughly the size of a typical city. It is quite possibly the densest material possible in the entire universe, balancing just one tiny step away from becoming a black hole.
And because of that insane density, the surface environment is just a sensory nightmare. The gravitational pull is so strong here that light itself can be bent into circular orbits right around the star. If you tried to climb a mountain on a neutron star, well, you wouldn't get very far. The intense gravity literally flattens the tallest mountains to fractions of a millimeter high. And remember the conservation of angular momentum? Just like an ice skater pulling their arms in to spin faster, the collapsing star speeds up dramatically. Some of these objects, which we call pulsars, can spin at a dizzying 43,000 revolutions per minute. No way, right?
Part 3. Anatomy of a neutron star.
Believe it or not, it gets even weirder when we look inside this exotic stellar corpse and see what happens to matter under these impossible pressures. The internal structure of a neutron star tests the very bounds of modern physics. At the outer crust, you've got highly compressed electrons, but drop down into the inner mantle, and the extreme pressure forces the neutrons to form microscopic, truly bizarre structures.
Physicists actually refer to this as nuclear pasta because these dense clumps form tubes just like spaghetti or lumps like gnocchi, and at the very core, it's a completely uncharted soup of quarks and gluons. It's a state of matter unseen in the wider universe since the very earliest moments of the Big Bang.
Part 4. The Kilonova collision.
So we have these incredibly dense, hyperspinning, pasta-filled, city-sized spheres of extreme gravity. What happens when two of these absolute monsters find themselves locked in a binary orbit, just circling one another? Well, this is where the story of your gold jewelry truly begins. As these two super-dense objects spiral inward toward each other, they definitely don't do it quietly. They bleed energy directly into the fabric of space itself. They emit a hum of gravitational waves, actual physical ripples in spacetime that propagate out into the universe like waves in a pond. As they lose energy through these waves, their orbit shrinks, drawing them closer and closer together until they inevitably and violently crash.
Now, what's really interesting about this timeline is that it's not just a mathematical theory anymore. In 2017, humanity actually witnessed one of these events. Let's break down this historic multi-messenger event. Seconds before the collision, a worldwide network of detectors physically felt those gravitational waves wash right over the Earth. Then, almost perfectly simultaneously, telescopes caught the flash of a short gamma-ray burst from the collision itself. And for weeks afterward, astronomers across 6 continents tracked a glowing, expanding debris cloud. It was incredible. We heard the ripples in gravity and we saw the flash of light.
And right there, within that glowing debris cloud, we finally found the cosmic forge. The collision of 2 neutron stars, which astronomers call a kilonova, creates conditions so unbelievably extreme that it forces neutrons into atomic nuclei faster than they can decay. This specific 2017 event created a debris cloud incredibly rich with heavy elements, including several Earth masses worth of gold alone. This right here is the factory with the energies needed to fill out the heaviest parts of the periodic table.
And this brilliantly illustrates the staggering scale of what we're actually dealing with. A single collision between 2 city-sized stellar remnants, happening in a fraction of a second, synthesized multiple entire Earth masses of pure gold. It was blasted out into the interstellar medium where it'll eventually cool down, mix with swirling gas clouds, and perhaps one day participate in the next round of planet formation. Over billions of years, a tiny fraction of that gold found its way into the crust of our early Earth, and eventually onto your finger or around your neck.
So, the very next time you look at a piece of gold, take a second to remember the incredible story it tells. It is literally the frozen shrapnel of dead, exotic stars that collided millions of light years away. Pretty cool, right? But it does leave us with a provocative thought. If just one kilonova collision makes multiple Earths out of gold, what other rare, completely undiscovered elements might be hiding out there in the cosmic symphony, just waiting for our gravitational wave detectors to hear their song? Keep looking up, keep asking those big questions, and I'll catch you in the next explainer.